What's up, everybody? We are live. If you are watching this not live, it is currently 3:43, and we will start at 3:50. So, I was just about to write that with a Sharpie on my web. That was a close one. Starting at 3:50. Okay, it is 350. So let's begin. Now, the 2020 B3, this is a great problem in my opinion. Okay, that's subjective, but it's a great problem from the 2020 exam. I did not actually solve it on the exam, unfortunately. I actually only got 1 out of 60 on the B section, which is, that's okay. But I was able, I took a look at it, started looking at it a couple months ago, maybe last month, and I was able to solve it. Granted, it took me longer than 3 hours total, but I was able to solve it. So we're going to really dive into this problem, really dig into it, and I'm going to present 3 different solutions. All of them have a common thread, but they all have a slightly different approach. And all 3 of these solutions are, great solutions to this problem. So without further ado, let's begin. So first, we'll do, the first solution will be my approach. So what I have here is my work for the problem. And I'm basically going to explain my thought process for this problem and how I arrived at the solution that I did. Now, this is by no means, when I say this is the first solution, this is by no means like the best solution, okay? In some sense, it might even be, well, it really depends on, how good a solution is, really depends on who you are as a person, like what you're more likely to think of, right? Anyway, I'll just go ahead and start. So the problem is, if you haven't looked at it yet, the problem is let x naught equal 1 and let delta be some constant satisfying 0 less than delta less than 1. Iteratively for n equals 0, 1, 2, etc., a point xn plus 1 is chosen uniformly from the interval 0 to xn. Let z be the smallest value of n for which xn is less than delta. Find the expected value of z as a function of delta. One thing I really like about this problem is it's not too hard conceptually, I would say. Well, again, that's subjective, but it's really not and it doesn't seem that contrived either. It seems like an interesting setup that has an interesting answer, and it does. So the idea is we have the interval 0 to 1. Okay. And then we have some delta from 0 to 1. Okay, some delta between 0 and 1. Now, x naught we set equal to 1. And then we pick x1 is chosen uniformly and at random from this interval. So x1 is just some random point. Let's say it's here. And then we pick x2 randomly from 0 to x1. Let's say x2 is here. And then we pick x3 randomly from here. Let's say x3 is here. And then our goal is to find basically what is, on average, obviously there's an infinite number of combinations you could do here. On average, what will the first n be such that x of n is less than delta? In this case, it's 3. And we want to find that as a function of delta. So given a delta, we want to find this expected number of iterations it'll take. So the first thing that I thought about, well, first I kind of wrote some questions, some guiding questions to think about, how I wanted to proceed. Okay, just like guiding questions. So the first question is about the structure of the problem, the structure of the conditions. So how does this choosing process behave? Okay, very broad. Basically, when I'm, how does the process behave? How does it work? How can we visualize the set of the possibilities and the process itself? What are some important properties of it? The second big kind of question is about the condition. Okay, so it has to do with, in this case, the expected value function. Okay, so what I'm going to do is define f of delta as the function we want. Okay, so f of delta, it takes delta as input, and then it's going to output the expected number of moves it'll take, or n, expected number of n it'll take to get xn less than delta. So what does f of delta look like? Okay, what are some important characteristics of the function? How can we compute it? What can we relate values of f of delta for different delta together? Okay, and then 3, simplicity. It's not really a question. It's just like a statement that basically says there is a relatively simple and logical solution, okay, and logical choice for f of delta. So these three things, structure, condition, and simplicity, these are three things I kind of asked myself at the beginning, and the simplicity is more a reminder to myself that there is, with all these Putnam problems, or at least the ones that are, maybe the first three on each side, there is a relatively like clever or simple solution. If you're going down this really convoluted path, you're probably on the wrong path. That's important to keep in mind. Okay, so first, let's think about what this f of delta looks like. Let's think about some extreme values. Now, let's draw. So here, this is 0. This is 1. This is like the delta axis, okay? And let's think about how f of delta behaves. So when delta equals 1, then no matter what you choose for x1, that first one that you choose, it's always going to be less than delta, okay? So f of 1 equals 1. Let's say this is, the axes aren't really to scale, but that's okay. So f of 1 equals 1. Now, f of 0, this is kind of interesting. So as delta gets smaller and smaller, it's going to take more and more choices to get less than delta, to the point where when delta is 0, we're going to have actually a vertical asymptote here. So when delta, when delta is really small, it's going to take a lot of n. And of course, if delta is exactly 0, then it can't work. So we know that there's a vertical asymptote here, okay? And we also know that f of delta is a decreasing function. So as you increase delta, it's going to always, on average, take less moves to get less than delta. So when it's a decreasing function, it has this vertical asymptote here, and it looks something like that. Okay, so this is the first thing that I did. I kind of drew a graph of what it is. So now let's make some conjectures about maybe what this function is. Now this vertical asymptote hints at possibly that f of delta is 1 over delta. Also because f of 1 is 1, right? So that lines up. Or, in general, it could be 1 over delta to the k, where k is some power, okay? But it has this 1 over delta behavior. Now, if you think of another function which has a vertical asymptote, that would be ln of delta, okay? But this would be, ln function, you have to transform it a little bit in order to get it to look like this. And that would be 1 minus ln delta. If that's unclear, just ln delta, then you do a, reflection over the x-axis and you move it up 1. So this is also another possibility. And we could also have like ln delta to the k, I guess. We could have like powers here too. We could have 1 minus ln delta squared, or I think that's true. Something like that, okay? Not super important. All we're doing here is getting an idea of what we think this function will look like. So we kind of know what to look for once we get there. Now, so what I realized was like, there's really not any other choice, or at least I can't think of any other choice that doesn't look something like this. And if you think about all like the types of functions that have vertical asymptotes, the only way you can really produce a vertical asymptote is if you have this inverse behavior, or you have an ln delta, which at its core, the derivative of ln delta is 1 over delta. At its core is like this inverse delta behavior. So I was pretty confident going in, like, okay, my function that I'm going to get is going to look something like this. All right, but now let's go ahead and actually try to solve this problem. So what I did was I broke it down. Now f of delta is an expected value. So what I did was I said, okay, expected value, that's the sum of the probability of an event times the expected number of moves of that event, right? So what I did was basically said, this is going to be a sum from n equals 1 to infinity. And so the probability that it takes exactly n moves times n. Okay, that's just expected value formula, basically plugging it right in. And so the goal becomes, can we figure out what P of n is? The probability takes exactly n moves. And then, of course, hopefully later we can evaluate the series. Now, with this goal in mind, I went ahead and tried small cases. So P of 1. P of 1 is naturally the easiest. If you have this interval from 0 to 1, and here's your delta threshold, okay? The probability that x1, if it's chosen randomly from here, probability that x1 is less than delta is just delta, okay? So P of 1 is equal to delta. It's in this range, right? Now, let's think about P of 2, a little bit harder. Now, P of 2 is going to be, well, we need to make sure, first off, we need to make sure that x1 is greater than delta. So that occurs with probability 1 minus delta. Is there glare in the, no, it's okay. And then given x1 is a certain value, the probability that x2 lies in the correct range is going to be delta over x1, depending on what x1 is. So what that means is we're gonna have to do an integral, okay? Because we're gonna have to integrate over all the possibilities for x1. Here, let me make sure that this is this looks right. So, okay, yeah. So if we instead write it more formally using an integral, what we have is that P of 2 is equal to the probability that x1 is greater than delta times, then we integrate from delta to 1. So these are all the possibilities for x1 that we're considering. And this will be, okay, first, the probability that x2 is in a certain block. So wait, let me think about this a little bit. Okay. So there's a delta over x1 probability that x2 lies within like the correct. There's a wait. I apologize. Okay, so there's a delta over x1 probability that x2 is going to lie within the correct range, okay? And then we multiply by dx1 over 1 minus delta. Now I'm trying to remember how I can explain this really well, but okay. So what we're doing here is saying that the probability that x1 here, let me rewrite this. So the probability that x1 lies in a specific little range, okay, of length dx1 between delta and 1. You may think, okay, that's dx1 because the interval is 1, but we're looking only from delta to 1. So this is dx1 over 1 minus delta. So this is the probability that x1 lies in a very specific range. And then times, given x1 lies in this very infinitesimal, specific range, probability that x2 is less than delta is delta over x1. Okay. So that's what we get for P of 2. Then you can see the 1 minus deltas will cancel. And so what we're left with is P of 2 equals the integral from delta to 1. And again, we're integrating over x1. Delta to 1 of delta over x1 dx1. And so this is just like, 1 over, that's, the blur is really bad, but hopefully you can see the integral in there. And this will evaluate to delta ln x1 evaluated at delta and 1. And then this becomes delta minus delta ln delta. So that's P of 2, minus delta ln delta. Now again, at this point, we really, all we're doing here is really trying to get a feel for how this works and trying to see maybe if there's a pattern. Okay, so the first one, P of 1 was delta, P of 2 is minus delta ln delta. Don't really see a pattern. You can't really make a pattern out of two things like that. So what we should do next is P of 3, right? Now P of 3 takes a while. You got to be careful. I'm not going to do it here. It turns into basically a double integral with x1 and x2, but I'm not going to belabor the point. What you end up getting for P of 3 is, let me ensure. You end up getting 1/2 delta ln delta squared. You're getting this. Okay. And also another thing we could do, which is something you should do, is once we get this result P of 2, let's make sure that it actually makes sense. So when delta equals 1, P of 2 is 0, which makes sense because when delta is 1, then you're always going to get it in one move, right? And if delta is actually, as delta approaches 0, P of 2 will approach 0. And you can get that from L'Hopital's rule. And the same is true of P of 3. So that's what we get for P of 3 when we do like this double integral. And at this point, I guess, now again, my work is a little messy, right? Because it's very nonlinear, right? Sometimes you hit dead ends and stuff. I tried to continue this to try to induct, using integrals. It wasn't really working super well. But eventually I made a very, very key insight, which is going to be central to all three solutions that I'll present. The insight is the following. If I want to, now ultimately what I was trying to do here was something kind of inductive, okay? Now if I think what is P of n plus 1 in terms of P of n? What I can do is, so here's 0 to 1, here's delta, and here's x1. Now, P of n plus 1, or at least the key thing is to realize that the probability that it takes n plus 1 moves to get less than delta is the same as the probability that it takes n moves after this point to get delta. And what we can do is treat this interval as an entire interval of length 1. We can linearly scale this, and the process is the exact same. So if we do this scaling, what ends up happening is, so what we imagine is we're expanding this to where x1 is 1, okay? Then delta becomes delta over x1. So to reiterate, this process here, right? The odds that it takes, or the probability it takes n to get less than delta after this point, we can think of that process, everything after the first choice, as a process which takes n moves where x1 is 1 and we're using a bigger delta of delta over x1. So what that means is here, we're going to have an integral. x1 could be anything from delta to 1. And then given we know what x1 is, okay, well, I guess first off, the probability that x1 lies in any specific range is just dx1. And then given that x1 lies at a specific value, then the probability that it takes n plus 1 moves in total is the same as the probability it takes n moves after this point, which is the same as P of n, but we're using delta over x1. We're using this bigger delta. So P of n plus 1 comma delta is equal to dx1 times P of n, but using delta over x1. Using delta over x1. This idea is really key, and I'll probably go over it a couple more times as well. This is really where all of the solutions really center on this, and I'll frequently, like I said, I'll revisit it. So now we have this integral we have this recursive definition for our probability. Just to rewrite it, just to rearrange it a little bit, you have P of n plus 1 delta equals the integral from delta 1 to 1, P of n delta over x1 dx1. And the base case is that P of 1 comma delta is always just going to be delta. What's nice about this is once you start plugging it in, okay, you just you do the same kind of process we did before, except it gets a lot quicker. You get the same value for P of 2 and you get the same value for P of 3. So when you're actually solving this problem, if you solved it exactly like I did, which is highly unlikely, but you kind of got the initial values in an inefficient way, you found a more efficient way, but the inefficient way was still not a waste of time because now you're more confident that this equation is correct. But anyway, once you start doing this, right, and you get up to P of 4 is, okay, let me write out P of 1, 2, 3, and 4 and see if you can notice the pattern. So P of 1 is just delta. P of 2 is minus delta ln delta. P of 3 is, hope the glare isn't, okay. P of 3 is 1/2 delta ln delta squared, and P of 4 is equal to minus 1/6 delta ln delta cubed. So the pattern is, just take a look at it, okay? First off, there's alternating signs, okay? So it's positive, negative, positive, negative. Well, okay, it's not actually negative, right? The probability is not negative, just the sign is negative. So we know there's a minus 1 to the power of n in there. This delta here, there's always this factor of delta, okay? The ln deltas, they increase in power. So this is power 1, power 2, power 3, and then power of 0. And these coefficients, now it may be hard to detect this if you haven't really seen this frequently, but whenever you have these coefficients where it's like 1, 1/2, 1/6, that should hint to you of factorials. 1 factorial, 2 factorial, 3 factorial. This would also become apparent when you're actually solving the integral, like when you're actually finding P of 4, that also becomes apparent that happens. So our conjecture, what we can do is take all of those, take this pattern and all of the sub-patterns that are going on, we can make a conjecture for what we think P of n is. The conjecture is that P of n, and actually what I'm going to do is express P of n plus 1. The reason I do this is because here the power is 1 less, the factorial is 1 less. So if I do P of n plus 1, it's easier to express, okay? But anyway, the pattern or the conjecture that we have, I guess it'd be P of n plus 1, is equal to minus 1 to the n over n factorial times delta ln delta to the n. That is what the pattern seems to suggest. Okay. And now let's go ahead and prove it. Now, obviously, for n equal to 0, we get P of 1. You plug it in, everything works out. So the base case works. Now we need to show that it satisfies the integral that we found. So we're going to assume P of n, and we're going to show P of n plus 1 is this form. So P of n plus 1, comma, I guess delta, is equal to the integral. The blur is probably, yeah, that's okay though. Delta to 1 of I guess if you're really doing like an induction, you assume you assume it's true for k. That's just really not that important, but it's good to be detailed like that. P of k, comma delta over x dx. Okay, that's the integral that we got. Now, we know what the formula for this is, or at least that's the inductive hypothesis. So let's go ahead and plug it in. we get -1. Well, and I'm going to plug it in and also pull out the non-x dependent terms. So we get -1 to the k over, or k minus 1 over k minus 1 factorial, then times delta, So -1 to the k minus 1 over k minus 1 factorial. Then we're integrating from delta to 1, and it becomes delta over x times ln delta over x dx, or ln delta over x to the k minus 1. All I did was plug in here, okay? Plug in the conjecture that we had. Then I'll further simplify this a little bit. So I'll pull out the delta and I'll expand this ln. Whenever you have an ln of division, a lot of times it's useful to write it as a subtraction, right? And I'll pull out the delta. This is getting a lot of variables going on, but see, what's kind of ironic is that this is in general. A lot of times people think that the algebra, that this part with all the variables and stuff is the most confusing part. Really, the hardest and most confusing part is the conceptual initial thing you find out. And this is all I'm doing here is evaluating an integral, okay? And it's actually not too difficult to evaluate. It cleans up with a nice U substitution. Anyway, it was a bit of a diversion. But here we have ln delta minus ln x to the k minus 1 dx. So this is our integral. You may notice, I hinted at it, U substitution. If you U substitute for this inner part here, du is -1 over x dx. We have this 1 over x dx. So when we U sub, this will simplify to just a integral of u to the k minus 1, which we know how to do, right? Which is great. It's great that it simplifies like that. It's always a nice feeling. So continuing further, this simplifies to -1 to the k minus 1 over k minus 1 factorial times delta. Now u is ln delta minus ln x. Well, I guess here I'll just keep the bounds here. X equals delta and 1. We don't have to change the bounds as long as we remember that they're in terms of x. And then we get, now this is important. So u is ln delta minus ln x. Du is -1 over x dx. So we get an extra minus sign when we sub in the du. That extra -1 we can throw up here. Change -1 to the k, -1 to the k minus 1 to -1 to the k. The reason also I do that is because we know we're aiming for a -1 to the k in the final answer, right? But anyway, bit of a diversion. This becomes u to the k minus 1 du. I know it's kind of small, so I'll write bigger next time. Then we just do the basic, integrating power rule, reverse power rule, whatever. U to the k over k. And then isn't this satisfying, right? The k and the k minus 1 factorial compress into a k factorial. And the u, oh yeah, and we're evaluating this at x equal to delta, x equal to 1. So this becomes -1 to the k over k factorial delta, and then times, okay, ln delta minus ln x to the k evaluated when x equals delta and 1. And then when x equals delta, this is 0. And when x equals 1, this is just ln delta and then to the k. So what that means is this simplifies to ln delta to the k. And that completes the proof by induction, because this is exactly what we're aiming for. So great. We found our expression, right? This is the big first half of the solution. The next half is we actually have to evaluate the series that we initially set up, right? So what we want to evaluate is, which is f of delta, is the sum from n equal to 1 to infinity, or I'm going to use m for reasons that will become apparent in a sec, m equal to 1 to infinity of m times p of m, just the expected value formula. Then, well, what I'm going to do here is instead of writing m, I'm going to write m plus 1, and I'm going to shift the bound. There's two reasons I do this. The first is that p of m plus 1 is like, we talked about this. P of m plus 1 has all the powers in terms of m. It's a lot nicer to write p of m plus 1. The second is that when we make this lower bound 0, what I'm kind of looking to aim to do is to express this as like a Taylor series or like a power series. And power series, Taylor series, they all start with index 0, right? So there's a couple reasons that I do that. So this is from n equal to 0 to infinity. M is n plus 1. And then p of n plus 1 is minus 1 to the n over n factorial times delta ln delta to the n. Now I got kind of stuck here because this is kind of gross. At least it looks kind of gross. But there's a couple ways that we can make our lives easier in actually being able to evaluate this. So like I said, I kind of beat around the bush. I eventually got the answer, but then I found out a more direct way to do this. So the first thing we want to do, okay, like I said, my initial strategy was to write this, to think of this as a Taylor series. So what I wanted to do was basically pull the derivative like if you want to find the function which describes a Taylor series, I was like, okay, I can find all the derivative information. Like I can pull all the derivative information from each of the terms, and from all that derivative information, try to figure out the function. Now that's a really, not a really bad, but it's not a great way to go about evaluating a series like this. The better way to do it is to express it in terms of known power series, okay? To simplify this to things that we know. First off, it's important to note that the variable that is actually being powered in this power series is not delta, it's ln delta. And to make our lives a bit easier in terms of like looking at this, I'm going to substitute alpha equal to ln delta. So it looks more like, the power series. It's easier to recognize power series that we already know. So this becomes this, and then minus 1 to the n times n plus 1 over n factorial. Then delta becomes e to the alpha, and this is alpha to the n. Okay. Now this e to the alpha, which is again just ln delta, we can pull that out. Okay, that's a constant. So we can pull that out to make this less messy. Okay. You can't really see that well. Okay, e to the alpha. And then we want to find this. So, the next step is, after looking at this for a while, I feel like there's really only one thing you can do, okay, when you look at this. Okay, if you pause and think about it, okay, there's really only one simplification you can make here, and it's to expand out this n plus 1, right? To expand to make this two terms. You're at a dead end otherwise, right? And it turns out that is what you're supposed to do, which when you take a step back, that makes complete sense, right? Like there's only one thing we can do, and it is the thing that makes sense to do, right? So, and once you realize to do that, what you should notice is that the first term so the term with the n, that's going to cancel with the n factorial and make an n minus 1 factorial, okay? And the next term is just going to have an n factorial. So that's going to maybe I'll just go ahead and do it. Maybe I'm describing my thought process too far down the line, but I'll go ahead and do it, and you should be able to see how this simplifies. So this becomes okay. So this becomes e to the alpha times Oh, you can't really see that because of the blur. There's an e to the alpha out front, times then the sum from n equal to 0 to infinity of minus 1 to the n over n minus 1 factorial. So that's the first term with the n. The n cancels with the denominator, making n minus 1 factorial. Alpha to the n. Then, oh, the blur is covering up whatever. It's just a sum, okay? Sum from n equal to 0 to infinity, minus 1 to the n over n factorial, alpha to the n. Okay. Now the second sum here, this should look hopefully familiar. This is just going to be e to the minus alpha. So the way you see that is, you know, this is like minus alpha to the n over n factorial. And that's going to be e to the minus alpha. Taylor series for e to the x. Super common, super important. So this second term here is e to the minus alpha. So all we need to do is find out this first sum, which is inconveniently blurred out a little bit. So let's go ahead and do that. Now, the problem with the way that this is written is, like, if we want to apply the e to the x power series, it's really important that this is an n factorial in the denominator, okay? Like, yeah, we need to make sure that this is an n factorial in the denominator. The reason that that's more important, like, okay, technically we need all of these terms to have powers of n on them, the minus 1, the alpha, and the n minus 1 factorial. We need all of them to have, like, n's on them. But the minus 1 and the alpha, like, to shift their powers, all we need to do is multiply by minus 1 or multiply by alpha. Like, we can just pull out factors, add on factors super easily. This n minus 1 factorial, though, we can't, like, multiply by n to every term because n is changing, right? So that's the one that we need to shift the index to account for. So what we'll do is like I said, we'll shift the index. So we're going to write this as a sum from, now, okay, kind of going all over the place, but n equal to 0, this creates a problem. This creates a minus 1 factorial. But if you look back at the original kind of setup for the sum, this n equal to 0 term doesn't matter, okay? Like, technically I should have case worked on it, and technically I should have fixed this at the very beginning. But basically, n equal to 0, term is 0, doesn't matter. So we can really just think of this as a sum from n equal to 1 to infinity, okay? That allows us to shift the bounds pretty more easily. So we'll shift down 1. This becomes minus 1 to the n plus 1, and alpha to the n plus 1 over n factorial. The minus 1 to the n plus 1, the alpha to the n plus 1, we're going to pull out a minus 1 and an alpha from those to make the powers n. So what that means is, when all is said and done, we're going to get minus alpha. Those are the extra minus 1 and alpha that we get. N equal to 0 to infinity of minus 1 to the n, alpha to the n over n factorial. Simplifies like that. Then this, like I said, is e to the minus alpha. Okay, we're trucking through this. This is good. We're almost there. The grand finale. Maybe you might hear my dog barking. It's okay. All right, so this is just e to the minus alpha. So what we get is e to the alpha times minus alpha, e to the minus alpha plus e to the minus alpha. And when you expand this bad boy out, okay, this becomes 1 minus alpha. And alpha is ln delta, right? That's the substitution we made. We get f of delta equals 1 minus ln delta. And isn't that satisfying? I called that, okay? I called that at the beginning. Okay, now granted, of course, when I started this presentation, I already knew that was going to be the answer. But when I actually solved this, kind of called it at the beginning. What's nice is, like, when I got this answer, I was like, okay, like, I didn't have to check if it made sense. I already knew it made sense, right? Because I thought about it beforehand. But that is how I solve the problem. That is my solution to the problem. A lot of algebra, a a lot of series and stuff, okay? But now this solution is more bulky than the next two I will present, but I also think that part of it is easier, like to think of like, oh, I'm going to write the expected value as the sum of like the probability that it's n times, n, like that step. And then, evaluating the series, that's just kind of like algebra. Like personally, I think that although the solution is bulkier, I had a higher chance of like getting to it. And I know that's like a dumb statement because I did, but I think you might understand what I mean. Sometimes often the shortest solution, the most clever solution, it's the most clever, so it's like the hardest to think of. And sometimes the longer solutions, which appear more complicated on the surface, are actually easier to obtain, right? Anyway, let's go ahead and discuss the second solution to this problem. And I promise the second and third are smaller, like I said. So what we will do is okay. First off, and I'll go over it again, the big idea that you can scale, like you can, given you pick x1 and you have a delta, that you can think of that as like a whole process with going from 0 to 1, like that scaling idea is going to be central to this as well. So first, what we're going to do is we're going to use the expected value formula, but we're going to use it in a different way. We're going to write f of delta as the sum, and it's the sum over like the probability of some event times the expected value of that event, right? That's like the general solution or general form of this. And that event, instead of being the number of moves it takes, we're going to make the probability basically the probability that x1 equals a particular value c, and then the expected number of moves it takes given x1 equals c. Okay? So what we're doing here is basically saying like, okay, over all the possibilities for x1 that I could get, okay, then given I have an x1, what is the expected number of moves it'll take given that x1 is this specific value? Okay. It's really not that contrived or anything to consider this question, I would think. Now, well, let's break it down. So what we're doing is saying, okay, well, yeah, let's break it down. So 0 to 1, here's delta, okay? And what we want to do is sum. First is the probability that x1 is some specific value. Let's say c. That's just dx1, okay? dx1. Then the next question, which is harder, is the expected number of moves it takes given that x1 is c. What we're going to do is call this g of delta, comma, c. Okay. So we're defining a new function, g of delta, comma, c, with the specific restriction that c is x1, or that x1 is picked to be c. And of course, this is an interval. So we get f of delta equals the integral. Now, x1 could be anything from 0 to 1, or c could be anything from 0 to 1. G of delta, comma, c, and then dc, or dx1. It doesn't, kind of the same thing, right? So we get this equation. Now, what is g of delta c? This is really a piecewise function, okay? If c is less than delta, then g of delta, comma, c is going to be 1. Because the reason, basically, you're saying, okay, if x1 is less than delta, if we know that x1 is less than delta, then like the expected numbers it takes is 1. We know that for a fact. Okay, so 1 if c is less than delta. Now, if c is greater than delta, what we're going to do is we're going to do the same like scaling idea. So let's say c is some value greater than delta. Okay, then what it's going to take 1 plus, and then you imagine, okay, let's say x1 was at 1 and we scaled delta to be at delta over x1 or delta over c, right? Then it's going to take f of delta over c at that point. So we have the first pick is x1 equal to c, plus the number of extra picks is going to be basically it's going to be f of delta over c because we scaled the process and thought of it as the original process, if that makes sense. With all these solutions, if you're hearing this for the first time, look, the solutions are, if you go into like AOPS.com, like the forums, if you look up 2020 B3, you can kind of find these solutions. This is also the actual official posted solution. If you're hearing this for the first time, it might be kind of complicated, a lot to take in. You're going to have to go and break it down a little bit yourself. But hopefully I'm doing at least an okay job of explaining it. But anyway, if c is larger than delta, g of delta comma c is 1 plus f of delta over c, the new scaled delta. Okay, and with this in mind, let's go ahead and plug this in and get an expression with f of delta. So what we're going to get at the end is an equation involving f of delta and f of delta over c. So, okay, well, the first thing is that, well, no, I'll just go ahead and do it. So we can break this into two integrals, 0 to delta, and then delta to 1. Okay, then we use the piecewise definition. So this is just 1, so this integral is just delta. Okay, the second one, so there's a 1 plus. Now the 1 is going to just kind of, the bounds are delta to 1. So 1 plus some function, that 1 is going to turn into 1 minus delta when we split the integral in half and evaluate it. Okay, and then we get your integral from delta to 1, f of delta over c dc. And then, of course, this becomes just a 1. Okay, and you can also get this right away. Okay, you can get this idea right away if you think about like, okay, first I pick x1, and then the only cases I care about past that point are when x1 is from delta to 1. Otherwise, the process is terminated. And if x1 is from delta to 1, then the expected number it will take is f of delta over c. So you can get this directly, although like this little bit of algebra is not really a sticking point if you know what the equations are and stuff. Okay, that's part 1 of the solution. Part 1, the first half done, where we apply the scaling idea and we have an equation. Part 2 is solving the equation. And this is a weird equation. Okay, I'm not gonna lie, but we're gonna get through it. So, this is what we have. Okay. Now, what's weird? Well, here, let me look at my work. Okay. So what's weird about this is, well, okay. First off, in a normal situation when we have something like this, we have a function in terms of its integral. Okay. So usually we want to differentiate both sides because then we get a derivative in terms of its function, which just turns into a differential equation, right? The problem here, though, is that if we try to differentiate with respect to delta, okay, there's delta dependence in both the the lower bound, and the integrand itself. Okay. To make this a little easier, what I'm going to do is replace all of my deltas with x's and all of my c's with t's. So this looks more like, something that you learned in Calc 2 or something like that, right? Just to make it look a little more familiar. So if we take a derivative with respect to x on both sides, right, then normally when you take a derivative with respect to x, but the x is a bound in the integral, you just get the inner function. But there's also x dependence in the inner function. So what we want to do is, what we don't like is the x dependence in the integrand. That is what we don't know how to deal with. So what we'll do is just sub in to get rid of it, okay? So what we can do is set u equal to x over t. So u equals x over t, and then du equals, now this is du derivative with respect to t, du by dt, minus x over t squared, okay, dt. Now, this kind of bothered me a little bit because the x dependence is still there, but when you rewrite it, if you think purely in terms of u after you rewrite this, it is essentially gone, okay, from the problem. Basically, what we've done conceptually, the way that I rationalize this to myself, is you have x dependence in the lower bound and you have x dependence in the integrand. What we're doing by the substitution is basically consolidating all of that x dependence into the bound, okay, and this basically becomes it no longer has that problem, okay. Anyway, let's go ahead. This is also something I'll touch on later, but let's just go ahead and do it. Let's just see if it works, okay, instead of trying to conceptually really get it yet. Let's just try some algebra, see if it works. So what we'll do, dt is minus t squared over x du, right? And then t is, and then this just turns into a u. So when we make the substitution, this becomes 1 plus the integral from delta to 1. Now, let's go ahead and change the bounds, okay? So t is going from delta to, hold up. Oh, the bounds are from x to 1, right? Because we made the substitution. So t is going from x to 1, so u is going from 1 to, u is going to go from 1 to x, okay? Let me make sure that that's right. Yes. Okay. U goes from 1 to x. Then this becomes, so dt has all this stuff, okay? Then f of u du. Okay. And also, I guess, I kind of, what I should have done here is, to make the substitution easier, I should have written t equals x over u, and then dt equals minus x over u squared du. Okay, doesn't actually change the truth of the statement, just makes the substitution a little bit easier because we want to get rid of all the t's in the problem, right? Anyway, dt is minus x over u squared then times du, right? And then what's great about this is this x, it's not actually dependent on, it's the x is basically a constant in this, right? It's not basically a constant, it is a constant in this integrand. So what we'll do is we'll pull out the minus x, and this becomes f of u over u squared du. Okay, and turns out we were successful, okay? Because what you notice is that this integrand here is purely a function of u, some dummy variable, okay? And the only x dependence lies in this upper bound. So when we take a derivative of both sides, okay, we will be able to successfully get a differential equation, okay? That isn't, well, we know how to get a differential equation. So let's go ahead and do that. So we're going to take a derivative of both sides. Well, first thing, to make our lives easier, okay, if you just try taking the derivative, the problem is that this here, we have to use product rule on it, okay? And when we use product rule, that means that the integral ends up staying alive, okay? So what we want to do is divide by x through this whole thing. We want to clean this so that it's just this, and then when we hit it with the derivative, it completely goes away. The integral goes away. So we rewrite this as f of x over x equals 1 over x minus this integral. Hope I don't make a algebra mistake. Okay, boom, get that. Then we hit it with derivative. So this here, quotient rule, okay? So that's going to be derivative of f times g minus f times the derivative of g over x squared equals minus 1 over x squared minus, and then we hit this with the derivative, right? Super clean, okay, because the x is in the upper bound, so it's just this inner function. We plug in x. Fundamental theorem of calculus, right? Then we multiply through by x squared. Multiply through f prime of x, x minus f of x equals 1, or is that minus 1 or a 1? I think it's a minus 1. Yes, okay. And then, oh my God, even more satisfying, right? The f of x actually cancels. So we get f prime of x equals minus 1 over x. Okay, super nice. And of course, that means that f of x is minus ln x, right? No, wrong, okay? Plus c, all right? Never forget your plus c's. And the way we find c is we know for a fact, f of 1 is 1. We talked about this. F of 1 is 1. So then f of 1, which equals minus ln 1 plus c, is equal to 1. So then c is 1. Okay? Not super easy. I mean, it's easier than this whole thing. So c is 1, and we obtain f of x is 1 minus ln x, or f of delta is 1 minus ln of delta. Same answer as before, right? Same answer as before. I like the solution too, honestly. And what I like about it, well, part of what I like about at least a big part of what I like about the solution is that at the very end, you don't actually have to, it looks like you're going to have to solve a differential equation, but you don't actually have to. Like, you could do this with Calc 2 knowledge. You know what I mean? So I think I like that, and that's something that's nice about a lot of Putnam problems, at least a lot of the earlier ones, is that they don't really require that much advanced math to actually be able to do. So you can be relatively inexperienced in a lot of higher math, like me. I don't have that much experience. Like, I actually haven't even taken differential equations yet. I'll take it next semester. But even though I don't have all that knowledge, if I can solve I can still, solve the problem. Okay. Lastly, let's do solution 3. Solution 3 will be very similar to solution 2, but with a bit of a twist to it. So as before, we're going to write f of delta as the sum of the probability of some event times the expected value of that event, right? Expected value formula, okay? I know that's disgusting, but you heard me say it. So what we're going to do is not just find f of delta, but we're going to define basically this new function, f of delta comma x, where f of delta x is the expected number of moves it will take given x naught equals x. Okay, so we really want to find f of delta 1, f of delta comma 1. But making this more general function is going to help us. It's going to make it easier for us to get an equation, and we can also use the same scaling principle to relate values of this function together. Okay, so we're defining this general function f of delta comma x. Now, what we'll do is we're actually going to sum over the same event, okay, that we did last time. Oh no, my one viewer left. That's tragic. That's okay. So we're going to sum over the same event. That event is the probability that x1 equals t and times the expected number of moves given x1 equals t. Okay, so I use t here instead of c. Doesn't matter. Okay, it's the same idea as before. Okay, so the sum of the probability that x1 equals a specific value t times the expected number of moves it'll take given x1 equals t. Alrighty. So now what makes this, like I said, right? This general function, you may think, oh, I'm just making my life harder. I have to find something more complicated. But it makes writing this equation easier, okay? Because we have this more broad function that we can just plug into this equation. We don't have to adjust the parameters. We don't have to do the scaling beforehand. We can get an equation pretty directly. But anyway, so P of, I'm writing really big today. P of probability that x1 equals t, you may think it's dt, okay? But keep in mind, we're choosing x1 from 0 to x, okay? Not 0 to 1. So 0 to x, so the probability that x1 is specific value t is going to be dt over x, okay? It's the length of that tiny interval over the length of the whole interval. dt over x. And then the expected number of moves it'll take given that x1 equals t is similarly a actually no, this is super basic, okay? Not super basic. Okay. Let me pull myself back there. We don't really have to casework as much, okay? Now the expected number of moves it'll take given x1 equals t, well, that's just f of delta comma t, right? We're starting, it's just going to be 1 plus, and then the expected number of moves it'll take given we started x naught at t, okay? I said that fast. So first one, x1, we choose it, that's a 1, then plus the expected number of moves it will take past that point, okay? So this gives us an equation, right? We also know, now of course, this equation is only going to really apply if x is bigger than delta. If x is less than delta, then f of delta comma x would just be 0 because x naught is bigger than delta, right? But that's really not going to complicate things that much. That's something we can easily account for. Let me do this. So we have this equation. Let's go ahead and write it in an integral form. So we get f of delta comma x equals the integral from 0 to 1, because x1 could be anything from 0 to 1, of dt over x, okay, times 1 plus f of delta comma t. Okay, then we can pull out this 1 here, right? Okay, we can pull out a 1 over x, right? And also this 1, wait, hold up. I think let me check my work. So this becomes oh, right. Okay. Oh, okay. I know what I did wrong. This upper bound here is x. Okay. X1 can be anything from 0 to x, right? So let's pull out a 1 over x. Okay. And then we'll split this. So it becomes that when we split. And then this here, this is just x. This becomes just a 1, just a flat 1. Okay. So, and of course, at the end here, not of course, just you can do this. At the end here, you see 1 plus this stuff. You can get this directly if you just think about like, okay, the first one, I pick the first one, x1, that's my 1. Then plus all the extra ones are going to be, if you write this as dt over x, okay, the probability that, you know, t is in a certain range is dt over x, and then times f of delta over t. So you can get this directly, like a little, or you can get this a little more like quickly. But in my opinion, like I said, this algebra is not a sticking point. So I kind of, you know, I think doing it this way is totally fine. Anyway, not really an important digression. But we get this equation, okay? And we can simplify this too. If you notice, like, see everything, if t is less than delta, like I said, if t is less than delta, f of delta comma t is just 0, okay? Just 0. So this lower bound, we can just set it equal to delta, okay? So everything from 0 to delta, if we split this integral in two, everything from 0 to delta, just 0, okay? All right. So that is my tissue is dying, okay? That is the first part of the third solution is getting the equation. The second part is solving it. Now we're gonna have to be a little more careful because this is a multivariable equation. Okay, there's two variables going on, so we're gonna have to make sure that we're taking partial derivatives here technically, so we have to be a little more careful. Now what we're gonna do is the same thing as before. We don't like this 1 over x being on the integral. We're gonna multiply everything by x to isolate the integral. So what we get is f is x f of x, x f of delta comma x is equal to x plus the integral from delta to x of f of delta comma t dt. And then we differentiate with respect to x on both sides. We use power rule here, or product rule here. So derivative of f times g plus f times the derivative of g equals 1 plus, and then the derivative of this with respect to x is just going to be the inner function when we plug in x, right? And again, the super satisfying function cancellation occurs in the exact same way as it did before. This cancels with this, and we end up getting that f sub x of delta comma x is equal to 1 over x. Okay, or is it? Shouldn't it be minus? Let me take a quick look at this. I think it might be minus. No, I think that looks okay. I think this is true. Okay. So that means that if f sub x of delta comma x equals 1 over x, then f of delta comma x, let's integrate respect to x, is ln x, right? Wrong. Don't forget the plus c, okay? Right? Wrong, okay? This is a multivariable function, okay? This constant is a function of delta, right? Don't forget your Calc 3 basics. When you integrate a multivariable function with respect to one variable, the constant is a function of all the other variables, okay? All right. Now, what is g of delta? Well, we can plug in some known values. So we know that when x equals delta, f of delta comma delta is just going to be 1, right? So if x naught is delta and your threshold is delta, then the first one is always going to go less than delta, right? So we know f of delta comma delta equals 1. So that tells you that 1 equals ln of delta plus g of delta. Okay. So g of delta equals 1 minus ln delta. So once you solve this out, you get f of delta comma x equals ln x plus 1 minus ln delta. And when we plug in x equal to 1, when x naught is 1, we get the magical 1 minus ln delta once again. Okay? And that concludes solution number 3. So that was I know that was a lot, but that was fun. Okay? That was just a lot of that was some good old-fashioned algebra. Okay? And that's okay. All right, so what I'm going to talk about now is sort of the motivation for a lot of these steps. Okay? So I kind of went through I went through the solutions, but now I'm going to explain how you could think of them, okay, potentially. Now, of course, I say this, but at the same time, the first solution took me a long time to get, okay, and the second and third I didn't even think of, right? And actually, those took me a long time to understand, okay. But at the same time, it's always good to try to pull the motivation that other people had, okay. So the most clearly, the most important centerpiece to all of these solutions is the idea that this process, which takes place from 0 to 1, can be thought of as any process which takes place from 0 to x1. You can scale it up and think of it as the same process. That is super central to all 3 solutions, and there's really no solution that doesn't center around that. Now, the way that you think of this, at least the way that I kind of, I'll kind of tie this to something that I was learning recently, which is I was reading something about how self-referentiality, okay, is it's this thing that produces a lot of weird stuff in math, okay? So if you think if you've taken set theory, okay, and Russell's paradox, okay, or the barber's paradox, a barber shaves everyone in a town who doesn't shave themselves, and then the question is like, does the barber shave himself? And it becomes a paradox. Okay. And also like Gödel's incompleteness theorem, which is a statement about how it's a statement about a lot of things. I'm not going to pretend to really know everything about it, but really that math as a whole can't prove its own consistency. Also, there are always statements that are unprovable. So you can't prove everything in math. Like there's always something you can't prove, okay, given the current tools, and all this kind of weird stuff, okay? And all of it lies in self-referentiality, okay? When an object or a process is defined in terms of itself, okay? It creates like this, almost like an infinite loop, right? And a lot of cool stuff kind of comes from that. The same is true of this problem and this solution, okay? So the idea for this scaling, so how could you think of like, thinking of this whole scaling idea? To find it, you want to search for self-referentiality in the process, okay? So the question you ask is, how can a sub-process be thought of as a whole process? Okay. This question can lead to all three solutions. If you can answer it in general, then you can express some process in terms of its sub-process with a couple added extra terms, right? But then in turn, you express the sub-process in terms of the original process. And this leads to, you're exploiting self-referentiality. This will lead to an equation which involves like the process, or it'll reveal something really important about it. And really, if you think about, especially the second and third solutions, that's kind of what we did, right? We thought of f of delta, which is the whole process, right? Referencing the whole process. And then the sub-process is from x1 to like thinking past the x1. But the sub-process we could write in terms of the whole process by doing the scaling. And all of that basically meant that we could get an equation involving the process, right? F of delta, with some slight modifications. So we're using that self-referentiality in order to get the solution. So, so this is a form of induction, okay? But it's much broader, and it's also much stronger. So, if you think about induction is really exploiting self-referentiality as well. So the whole idea of induction is expressing, something for n plus 1 in terms of something for n. And you're basically, here, let me just read what I wrote. Induction is purely dependent upon self-referentiality and the idea that a whole process, which is for n plus 1, is expressible in terms of a sub-process, which is like the thing for n, which is in essence the thing for n, a whole process itself, okay, with a couple modifications. That's kind of a hand-wavy way or a very abstract way of describing induction, but if you think about it, that's kind of what it is, right? And then also, I wrote that processes, this is more specific to this problem, but processes that occur on the real line are often exhibit self-referentiality through linear scaling. So any like process on the real line of picking numbers or adding numbers, multiplying numbers, whatever, you can always just scale all the numbers. You can stretch and compress the real line, and it's still like the real line, right? Like it doesn't actually change the information being conveyed. So especially in this case, in this problem, the idea that you can take that smaller interval and stretch it, that smaller interval of 0 to x1, and stretch it to 0 to 1 to get like the exact same process is really important and a big idea. But anyway, so yeah, processes that occur on the real line, especially ones that are similar to this problem, exhibit self-referentiality in that way. This is true, however, not always true for processes which involve like floor and ceiling functions, because like the floor and ceiling functions, they're integer at their core, right? So you can't like just because x, the floor of x is 2 does not mean that the floor of 2x is 4, right? If x was like 1.6, for example. Okay. So I don't know how much of a big idea that is, okay, but I'm definitely keeping it in the back of my mind. All right, so that's a big idea for the first. That's a big idea for like the first part to all the solutions is applying that scaling idea to get those equations. Now, the second, which is more specific, the second part's more specific to each of the solutions, is the actual evaluation of for the first solution, the summation, for the other two, the equations. Now for the summation in the first solution, let's see if I remember it. Yeah. Believe it looks like this, minus 1 to the n over n factorial times n plus 1 delta ln delta to the n. Oh my God, it's blurred out, okay? This is summation for the first one. Really, the motivation for evaluating this is, like I said, making that substitution, like alpha equal to ln delta, making that substitution cleans things up, makes things look more familiar. And then I think from that point, I mean, once you make the substitution, it turns into this, right? And then you can pull out the e to the u, or e to the alpha, I guess. Okay. And I think that past this point, at least personally, I feel comfortable in being able to go past this point. Like, I think that the solution follows fairly cleanly just by thinking about, like, what is the only thing that I can do here? And it's expand the n plus 1. And then once you expand the n plus 1, it turns into, like, the e to the x power series. Now, that's like a personal thing, okay? So, like, so I personally feel that if you showed me this, then I could figure it out, okay? It's totally fine if maybe you don't feel that that's the case. So you would have to convince yourself of ways to motivate the next steps. But like personally, like when you're reviewing a problem, you want to think about the motivation. Like you want to think about what are the big ideas, what are the big conceptual hurdles for you, and then at what point are you able to just be confident in your ability to just solve the problem? Okay, like just do the math and solve the problem. So you want to focus on like those sticking points, right? To for improvement. Okay. Like if I gave you, let's say you had some problem and then like it turned into like 3x plus 6 equals 9. Okay. Then you don't have to sit there and like think about the motivation for like, oh, I want to isolate x, or like I want to isolate x, so it makes sense to move the 6 to this side. And you don't have to think about that, okay? Because you know how to do that. At least if you don't know how to do this, I think you're in the wrong place, okay? I think the other stuff might be kind of complicated. But anyway, and also like I said, when I was doing the series, I tried to solve the Taylor series by finding the function from its derivative values, okay? So like I pulled, like from each of the terms, I pulled what the derivative was at 0. But like that's not that good of like a solution. That's not a super easy way to go about it, right? Because just because you know like, oh, I know that f of 0 is 1 and f prime of 0 equals 5 and f double prime of 0 equals 3. It's really hard to still find a function from that because you're still only being given 1 point. But anyway, I digress. So the main idea is, I know I'm kind of repetitive, but that's like how I review. I get repetitive sometimes. Main idea is when you evaluate a power series, first you substitute in for the variable, then you try to express the power series in terms of known power series. Okay, solution 2. For me, in understanding the solution, solution 2, like, well, I'll just explain where the big sticking point was for me. So you get this equation. I think this is right. Yeah. And then, like I said, I changed these to X's and T's just because, like, I don't know. I thought it would be easier on my brain. The sticking point for me here was like, so I knew that I wanted to take a derivative of both sides, and I knew that I could do it if this was a function of t, okay? But like, it has the x dependence in the integrand, and that's something that I really couldn't conceptually get over. That's something that I couldn't conceptually rationalize in my head. Like, how could I possibly take a derivative of both sides and evaluate it if this is also changing with x, right? That just makes things a lot more complicated. But really, the big mental change, and this is the big mental change that I needed to make was that sometimes it is better to just algebraically try something as opposed to trying to conceptually rationalize it all the time beforehand. Okay. So personally, when I'm solving a problem, and this is a good strategy. Okay. Well, at least I think it is. But a lot of times it's good to, you have an equation, to think about it on a conceptual level, like conceptually think about it, and then use that to guide your next step. Okay. That's a good way to wade through all of the algebra and the variables. And and this is like, and to gain intuition for what you're looking at. So one of the things that I talk about in a couple of my videos is the intuition formalization process, which is where basically when you first start a problem, you use your intuition. Then you have like an intuitive idea of how something works, and then you formalize it, okay, using like rigorous math. Then once you formalized it, that clears the picture, clarifies the picture more, and then you use intuition again, and then you formalize, etc. So there's kind of this back and forth between like getting these cloudy intuitive ideas and then formalizing them using math. And a big part of that is making sure you understand what's going on conceptually to get those intuitive ideas. But there's a problem with this, which is that, like, a lot of times, well, let me just read. Using your conceptual understanding of an equation or structure to guide your next decision is a great strategy, but sometimes you'll self-impose a conceptual barrier, okay? So sometimes it's better to just algebraically try something to see if it'll work instead of trying to conceptually intuit whether it will work and relying upon that intuition. Especially with complex topics, your conceptual assumption may be flawed, so don't trust it too much. So I should have just been like, okay, conceptually, I don't really know how to solve this, okay? But if I just pinpoint, okay, this integrand, the x dependence in integrand is what's annoying me, why don't I just substitute in a variable for it to get rid of it, okay? And then just solve it through, then I'd be able to figure it out, right? Okay. At the expense of repeating myself too much, I will succinctly, well, I know I'm repeating myself with this idea, but I really want to get it across, which is like, sometimes you don't need to know conceptually what's going on to make the next move. And sometimes when you try to conceptually understand what's going on, you're imposing a barrier where you're thinking about like, okay, will this work? As opposed to just, sometimes it's better just like try it and see if it works, right? Anyway, let's move on. So solution 3. Solution 3. The big idea with solution 3, once you get the equation, okay, so the equation is f of x comma delta equals 1 plus the integral from delta to x of f of delta comma t dt, okay? Now, personally, like, 1 over x. This equation isn't like, if you just, the idea here is to basically just remember your fundamentals. Calc 3, fundamentals, okay? Like, this equation, I don't think, like if you just kind of solve this, like, okay, well, first off, you have to know to multiply by x on both sides, okay? And then once you do that and like, you know, you solve this keeping in mind your Calc 3 fundamentals and like, oh, when I integrate a function with respect to one variable, then my constant is a function of of the other variables, right? Once you do that, you can solve it through pretty easily. The problem like that I got into with trying to do this, once I saw the equation, was that I was like way too high up in the clouds trying to think conceptually about like how to do it and how to guide my process and stuff. And I kind of forgot those fundamentals and it really confused me. So like, for example, when I got this equation, f prime of x delta equals 1 over x, where f prime is derivative with respect to x. When I got this and then I integrated and I got ln x, right? But I like forgot the, I added a plus c, but I forgot that this is really like a function of delta, which is something that you learn in Calc 3. Because I was just thinking too hard about it, okay? And I was forgetting my fundamentals. So big idea here, to solve this equation, remember your fundamentals, okay? Now I say Calc 3 fundamentals. I'm assuming that if you're watching this, you've done Calc 3 before. If not, you know, by fundamentals, I mean things you learn in class, okay? Yeah. Okay. So talked about just algebraically trying something out. Don't try to, sometimes it's better to just try, see if something works. Talked about being conceptually up in the clouds, okay? So sometimes when you're thinking how to do something conceptually, you're too high up in the clouds, okay? And you can't see something straightforward that's more on the ground, okay? In these cases, you want to try bringing it down to earth, okay? And the last mental change, that's not the last thing that we'll talk about, okay? I'll briefly touch on some extensions of this problem. But the last mental change that I personally am going to make is patience with uneasiness. So I haven't taken a prob theory class. My only experience with this kind of probability theory is through these problems. So I don't have that good of a foundation like with it. I don't feel super comfortable with it yet. And but one of the issues that I ran into when I was doing this problem was I was rushing some of those fundamentals. And I, like, you know, when you're trying to find a pattern, like when I was first doing it on the test, or the actual exam, when I was trying to find the pattern of P of 1, P of 2, P of 3, right? I made an algebra mistake somewhere in the integral for P of 3, or maybe P of 2. And when you're trying to find a pattern and you make a mistake, like you're totally not going to find that pattern, right? And so that kind of nuked my chances of getting the problem. So the lesson is in subjects or problems that you feel a bit uneasy about, or subjects you feel uneasy in, take your time and ensure you feel comfortable with what you've written down before you move on. That ultimately, that will save you time and energy down the road. And I also wrote this down, which is, I think, true. Patience has an incredible return on investment. Okay, that's a life lesson right there. That's not even a math lesson. Okay, patience has an incredible return on investment. What that means is that when you're patient with something, you may think that if you rush something, you're going to get it done quicker. But actually, if you're patient with it, you're going to make a lot better decisions. You're actually going to save a lot more time and energy in the long run. Okay, so investing energy into patience is going to save you a lot more energy in the end, right? Okay, so good thing to end the mental changes on a bit of a life lesson there, right? Okay, the last thing I will do is briefly talk about extensions to this problem, okay? Well, I guess the next thing in my review that I wrote was further study. So further study would be like probability theory. And then the next thing would be extensions. So some extensions to this problem, or at least the one I thought of, was like, what happens in higher dimensions? So what if you had, instead of a one-dimensional process, you had a two-dimensional process where basically this point here is 1, 1. Okay, so you're looking at the unit square, and delta is like some vector in the unit square. And you repeatedly pick, so like let's say I pick x1, it's there. Then I pick x2 in this range, let's say it's here. Okay, and then you basically pose the same question. As a function of delta, the vector, okay, how many moves will it take on average for you to get within this like within this delta rectangle? Basically within one of the coordinates of delta. So like if this point here is delta x, delta y, okay, this is a messy diagram, okay, do not do this. But if this point here is delta x, delta y, what I'm basically asking is like, if you repeatedly pick points in these squares, how long will it take until one of those points has either an x coordinate less than delta or a y coordinate less than x coordinate less than delta x or a y coordinate less than delta y? And then of course, you know, extending into like, what about 3 dimensions and 4 dimensions, right? And n dimensions, okay? What does that look like? Now, I wasn't actually able to solve this problem, like get a direct answer. I didn't, now granted, it's not, I didn't care that much. I just kind of was curious about like, how could I push this further? How far can I push this? What I did end up getting was that, interestingly, if you apply the same idea as solution 3, right, then you end up getting that. So let's say, wait, what did I do? Oh yeah, so let's say you define f of delta, comma, delta's a vector, f of delta, comma, p naught as the expected number of moves it'll take, given that you're using the vector delta, and p naught, you're using like some vector p naught. So like in the normal case, p naught is just 1, 1. But this is like a general case. And you can see how this is exactly the same, or very similar to solution 3, where we use not only an arbitrary delta, but an arbitrary x. But anyway, the question is, what is this function? Okay. And what it actually reduces to is the partial differential equation, which I have no damn idea how to solve, because I've not taken that class yet. Oh. Okay, reduces to this PDE. So you get P naught x, which is the x coordinate of P naught, times the derivative with respect to x, derivative of this function with respect to, x, then P naught y, Fy, and P naught x, P naught y, Fxy equals 1. Reduces to this differential equation, okay? And I mean, there is a solution to f. I don't really know how to figure it out, but, you know, there's an equation. And also, like, when you only have one variable here, then you can see how, like, okay, all of these y terms, they don't matter, right? So it just reduces to P naught x equals fx, which is fx equals 1 over P naught x, which is what we got in the one-dimensional case, right? Because P naught x was the initial x coordinate, or just x. But anyway, in general, the pattern is this. For the three-dimensional case, you get what you get is x, or so let's say this initial point we're just going to say is x comma y comma z, just to simplify things a little bit. Then you get x derivative with respect to x, y derivative with respect to y, z derivative with respect to z. Let's do plus xy fxy plus yz fxz fyz plus fxz fxz plus xyz f of xyz equals 1. Okay. So maybe you see the pattern. With this case, we have just one variable x of x, y of y, z of z, and then two variables x, y, f x, y, and then y, z, f, y, z, two variables, and then we have the final three variables. And I assume, I didn't actually figure it out, but I assume you could show inductively that for, in general, n dimensions, you get a very similar equation where first you sum all of the first variables, then you sum all of the pairs, and then all of the sets of 3, etc. And that massive differential equation equals 1. Okay, and that's what you end up getting at the end. Okay, so that was just a little extra bonus fact for you. All right, so that concludes our discussion of 2020 Putnam B3. I hope this not only gave you an in-depth understanding of the problem, but also of how to thoroughly review a problem and how to pull big ideas from it. So keep in mind, it took me about an hour and 42 minutes to present that, okay? Now, me actually reviewing it and solving the problem is probably upwards of 8 to 10 hours or something like that, right? But it's really important that, at least my opinion is that quality matters so much more than quantity. And really, you might spend 8 to 10 hours, okay, on a problem. But really what you're searching for is you're digging deeper and deeper and trying to find those really big ideas that you can apply in general. So for me, I think that the self-referentiality idea, I think that is something that I'm going to definitely use a lot more. And I think that, you do have to spend a lot of time with a problem to get those big ideas, which are really hiding under the surface and driving the whole thing. So thoroughly reviewing a problem takes time and patience. I'm not going to pretend it's easy at all. It's very easy to want to move on, okay? But ultimately, hitting those big insights and ideas is very satisfying, okay? And it's very useful. So thank you for joining me. As always, make sure to smash like and subscribe, and I will see you in a few weeks.